Alright, welcome back. So next thing we want to talk about is common divisors. So if you have two numbers, for example 36 and 12, we can write out the divisors for each of these because we know they're not prime. But we can also ask, what are the divisors that these have in common? For example, both numbers are divisible by 2 and 3 and also 6 and also 4. And well, it turns out in this case both numbers are also divisible by 12. So 12 is the greatest common divisor of these. That's not a horribly interesting example. But as another example, let's think about 40 and 18. So both of these have a common divisor of 2. Do they have any other common divisors? Well, we could find all the factors of 18. We could factor this. This is 2 times 3 squared. And 40 is 2 cubed times 5. And so we can kind of see that 2 to the first is the greatest common factor. But in general, we'd like a method for finding what the GCD is, the greatest common divisor between two numbers. And we do this typically when we're reducing fractions, right? If you want to write 40/18 in lower terms, you divide both top and bottom by the greatest common factor. This is 29ths. So there's a technique called Euclid's algorithm, which we can use to find the greatest common factor of any two integers. And even though this can work for negative numbers, I'm going to describe the algorithm for positive integers. And I'm going to insist that the order of the two numbers we're searching for a GCD of is very specific. So let's pick an interesting example. For example, 24 and 16. So find the greatest common divisor of 24 and 16. Alright, here's the algorithm. If you get this straight, it's very easy to use, but it's also very easy to sort of get things backwards. So take your first number, 24, write it as something times your second number, 16, plus a remainder. Okay, and you want as big a number as you can in front of 16. So 24 is 1 times 16 plus 8. Okay, now we take this number 16 and we write it as something times this remainder 8 plus something else. Well, that's easy. 16 is 2 times 8 plus 0. And once we get down to a 0, then this is the greatest common divisor. Okay, so let's do a larger example of this. So let's find the GCD of 735 and 252. So what do? We say 735 equals something times 252 plus something. Well, I'm pretty sure 252 goes in twice. It's not going to go in 3 times because that would be 756. So it's 2 times 252 plus something. So let's just put a little worksheet over here. 735 minus 2 times 252 is 504. So this leaves us with 231. Alright, bring the 252 over. And this is something times 231 plus something. Well, 231 is only going to go in once. And the remainder will be 52 minus 31. That'll be 21. Repeat. 231 equals something times 21 plus something. Alright, well 21, I don't know if that will go in 9 times. I think it will. 231, 21, it will go in 10 times. That's 210. 11 times, 21 times 11 will be 21, 21. There's 231. So this is 11 times 21 plus 0, which means this last remainder that we had, that's the greatest common divisor. So it's a totally mechanical procedure. We can think about why it works, but you don't need to understand that to be able to use it. But the basic why it works is that the GCD of 735, 252 will be exactly the same as the GCD of 252, 231. And you can write some modular equations to convince yourself of that. All right, so we'll find some GCDs in class. The next thing I want to mention is something called Fermat's little theorem. Fermat's little theorem. And it states the following: if P is prime and A is some integer which is not a multiple of P, then A to the P minus 1 is congruent to 1 mod P. Now clearly if A is a multiple of P, then A is congruent to 0 mod P, so any power of A is going to be congruent to 0, so that's not an interesting case. So in all interesting / reasonable cases, if P is a prime, any number raised to the P minus 1 is one more than a multiple of P. And we can use this to our advantage to do modular arithmetic, similar to what we did with modular exponentiation. We can use Fermat's little theorem. For example, if we wanted to find 7 to the 10th modulo 11, all we need to do is observe that that 7 is not a multiple of 11, right? So here we're setting P equal to 11 and A equal to 7. And Fermat's little theorem tells us directly that 7 raised to the 10th will be congruent to 1 modulo 11 modulo P. So without doing any work other than looking at this theorem, we can tell immediately that 7 to the 10th is one more than a multiple of 11. And that's pretty easy to confirm, right? If we use the BC command in Unix, we can say what is 7 to the 10th, and it's this big long number, and we can say 7 to the 10th minus 1 is this number, and if we take this number and we divide it by 11, it's exactly a multiple of 11, which means that the number that's one more, 7 to the 10th itself, is one more than a multiple of 11, so it's congruent to 1 modulo 11. So we'll play with Fermat's little theorem in class.